I didn't do a good job explaining this problem in the previous video, so I'm going to redo this problem again in this video. So a swimmer has dropped her goggles to the bottom of a pool at the shallow end, marked as 1 meter. So the goggles are at the 1 meter deep. So basically what I did, I just redraw this picture and I magnified it a little bit. Okay, so but the goggles don't look that deep. That's because of refraction. Okay, that's because of the refraction. Now here so how deep the goggles appear to be when you look straight down into the water, that's the question. Now we're going to use the Snell's law here, n1 sine theta 1 equal to n2 sine theta 2. Now the light ray is traveling from the goggle, so wherever you see object, basically the light is going to fall on this. Now the light rays are traveling in every direction. Okay, so say for example your eye is right here, so only few light rays are going to enter into your eye. Okay, so now that's what I'm looking at here. Okay, now here the light ray is coming from the object, so theta 1 is angle of incident, okay, and theta 2 is angle of refraction. Okay, so basically when the light ray travel from water to the air, it is going to go away from the normal. Okay, that's normal. Now theta 1 can we define here. So if you look at this triangle right there, I'm going to highlight this. This is the triangle we're looking at. Okay, I'm just highlighting the triangle. Okay, let me see. Okay, now that's the triangle. In this triangle, I know this length is x. Let me make this length is x, and that's 1 meter. So can I say tan theta 1 equal to x over 1, x over 1 meter. Okay, same way theta 2 here, so this is theta 2. Now if I extend this light ray straight back there, now what I'm doing here, I'm extending this light ray straight back there. So can I say here this has theta 2, this theta 2 and this theta 2 are same. So that's where we're going to see the virtual image. Okay, the virtual image is nothing but we feel like the object is right there, but in reality the object is not going to be there. Okay, so from there I can say tan theta 2 equal to I'm going to make this distance as d2. So tan theta 2 equal to x over opposite over adjacent, which is d prime. Tan theta 1 equal to tan. Okay, now once we define, I'm going to use the Snell's law here. Snell's law is n1 sine theta 1 equal to n2 sine theta 2. Okay, now he clearly mentioned in the question how do you, when you, so he in the question he clearly mentioned when you look straight down into the water. So we are looking straight down into the water. Basically this theta 1 and theta 2 are really small. When theta 1 and theta 2 are really small, theta 1 theta 2 are really small. If the for small angles, theta 1 is approximately equal to tan theta 1, approximately equal to sine theta 1. Same thing with theta 2 if they are very small angles. Okay, so I'm going to make that note here when theta is very small. So if you use the Snell's law, n1 sine theta 1 equal to n2 sine theta 2. So instead of sine, I'm going to use the tan theta. So n1 is 1.33 times x over 1 meter equal to n2 is air, we are using air, sine theta 2 is x over d prime. So x get cancel out, so d prime equal to 1 over 1.33, which is 0.75 meter. So basically the goggles are going to appear like they are uh, 0.75 meter deep instead of 1 meter deep. So basically that image we call it as virtual image.